Okay, good morning, everyone. Okay, it's nice to have the opportunity to be here to introduce our product. My name is Jimmy. I come from the Brooklyn. I'm the product manager of the nano indentation in the APAC region. So this is my pleasure to here to introduce about our technology about nano indentation. We call it nanomechanical testing. So I cannot speak Thai, so hopefully my English is good for you to understand. All right, this is my agenda today. I'm going to introduce our nano indenter technology from the Bruker hydrotron. And second part, I will talk about some our specific application and the more advanced nanomechanics testing functions. Then summary. I will continue my second talk that is about the high-speed mechanical mapping and the symphony solution. So let's start. So in Bruker, I think we are selling the nano indenter, that is for the nanomechanical measurement. But there is some signature technology from the Bruker that we always say the in situ nanomechanical instrument. So in situ is our mechanical testing philosophy. Every nanoscale testing must be based on the in situ technology. So if you don't have in situ technology, you will not know what you are testing and what is the testing result. I will show you the case later. Sorry. So this is the most common mechanical testing in the macro scale, right? So I believe there are many this kind of machine in the material science department, also for the dental department, medical engineering department. The tensor testing is very straightforward to test the sample, the material mechanical properties. This can shows, the result can show the elastic behavior. That's we can calculate the Young's modules. And also we can see the yield strength. That is for the strength of the material. So this is very common and very useful technique for every kind of material. Right? So another most common thing is to evaluate the hardness. We call it hardness testing. I think the most popular thing is the Vickers testing. That is Vickers hardness tester. They are using the probe to indent into the material and use the optical microscope to see the indentation mark to calculate the hardness. I think I have seen this machine in the dental department, no matter where, including the Mahidol University. So this is quite straightforward. They just use the indent to indent into material, and you will see how hard it is, right? But for the hardness tester, there is no way to get the elastic behavior like Young's modules from the tensor testing. So this is a well-known technology today. But in current technology, we have developed many different kinds of material. The scale is getting small and small. Just like we were saying that we are more focused on the micro and the nano scale. So I just categorize the different type of material for nanotechnology here. So if we look at the symphony is quite popular. This will be reported in my second presentation. But if you look at the symphony, I think we are using the symphony in many different industrial, like a semicon, display, data storage, or some hard coating for the protective film, right? So especially for the dental engineering, I think some the medical device, they have very concern about the surface. They need to use some special coating to protect. So the thickness is varied. Thickness can be nanometer, can be several 10 micrometer. So the synchronous will be the challenge for us to measure the mechanical properties. If this is very thin, it will be very, very difficult, right? Another kind of nanotechnology is about the composite material. So sometimes we mix the different material as one. We use the powder, we use the particle, we use the fiber as well. Different material mixed together, and the phase size will depend on how big if you mix material. Some particle size is based on nanometer. Some particle size more than 10 micron, right? So if we want to look at in detail for the mechanical properties between yellow and the blue phases, it also gives us the challenge for the lateral resolution of the machine. It's also about nano and the micro material. And the third part is about the metal and the alloy. The different grain size and different temperature are also the challenge. So I think those examples just tell us this cannot be used the traditional way to test the mechanical properties. That is the reason we are here to talking about the nano indentation. So nano indentation is the solution for the dedicated for the micro and the nano material. So the principle is quite easy. It's very similar to the Vickers indenter, but different. What's the difference? We are using the very high accuracy transducer, and this transducer can record the applied force and the displacement of the during the indentation procedure. So this is the diamond probe. The diamond probe is with known shape, and we can apply the force by our transducer and indent into the material and pour from the material. So during the indentation procedure, then we can get the displacement and the load curve from the transducer. And this is give us some good information about the mechanical properties. If we look at this, so our transducer output the load and the displacement. Displacement is just representative of the deformation from the material. And then the force is what we give on the tip, right? So this is totally about the mechanical properties response from the material. So we can use this curve to apply the content model, mechanical model from the Oliver Farr. That was developed from the 1992. Then we can calculate the elastic modules and the hardness here. So elastic module is defined by the contact stiffness divided by the area. So contact stiffness was defined by the slope for the unloading point. And unloading point also, the contact depth was also come from the Oliver Farr model. And hardness is quite similar to the Vickers hardness. This is the maximum force divided by the projection contact area. So the difference between the nano indentation and the Vickers indenter is that we can tell the customer the elastic behavior, just like Young's modules. We can tell the customer hardness as well. And why this is in nanoscale? Because the transducer must be very accurate. The displacement is accurate to below nanometer accuracy. Also, the force is very high resolution. This can be accurate about the nano-Newton resolution. So everything we are looking here is about the nano and the micro scale. And this is the video we are showing the nano indentation inside of the SEN. So this is the probe, just what I said, we indent into the material and calculate the contact area, then we get the elastic modules and hardness. So this is give you the image how accurate our nano indenter is. You see, this is the 5 micron scale bar. So the indentation mark is around maybe 5 micron, a little bit big. This is a larger indentation for the nano indentation. Normally, our indentation mark is below or just equal to 1 micron. This is very difficult to see by optical microscope. That is the reason we have to use the SEM. And this is what I am saying in the beginning, we call it in situ technology. In situ means that we can see what we are testing. Because we are working on the nano and the micro scale, this is not the scale can be seen from our eye or optical microscope. We need to use other in situ technology, right? So this is the work we are doing for the nano micro scale, for the elastic module, strength, for the hardness. And sometimes we are also calculate the fracture toughness by the nano indentation. I will explain this later, but this is the most common mechanical properties we are using the nano indenter to working on. So there is another example for the nano indenter on the same thing. So you look at this is our machine inside of SEN, right? We theater the angle, then we can see the indenter and the tip. So nano indenter, we can measure the hardness modules by the mechanical model, but sometimes we can see there is some strange signal from our force displacement curve. So this we call the pop-in signal. So if you look at the curve, it's very smooth in the beginning. Then when we see the pop-in, we see something happen. So this is cracking, and continue to measure. This is sparring here. That is representative of the material change. So the first pop-in is about the cracking. That is the fracture toughness, about the fracture toughness of the material. The second is about the thin film delamination. So this video just tells us, nano indenter can tell us not just only about the hardness and the modules. We can use nano indenter to see other mechanical properties as well. But the most important thing, again, still we need in situ image to help us understand what happened here, right? So this is our core technology we call the in situ nano indenter inside of the SEM. We call the pico indenter. This is the product developed by Hydrotron from 2010. So this is our product line. We call the pico indenter product line. So we also have the nano indenter inside of the TEN. This is down to the real nanoscale or Armstrong scale. We can use the TEN to see what's the mechanical properties and what is the inside of the material mechanical properties. So, okay, let's come back to the in situ technique. We are talking about the nanoscale for the nano indenter, right? So, we are using the SEN, TEN for the in situ. But what's about if we don't have SEN and TEN? If we like to see the micrometer indentation mark, we want to see the indentation mark below micrometer. This is not possible to see from our eye, even the microscope. If we don't have SEN, we still have the in situ technology we call the SPN or AFN. So in our company, we can use our nano indenter on the AFN. So we can use the AFN to scan the surface. We still can achieve nanoscale resolution of the surface. If you don't have AFN, we have standalone nano indenter. We will provide in situ SPN. This is scanning probe microscope technology. Very similar to AFN, but we use our probe. How do we work? we use the nano indenter transducer here, and we adapt the transducer with the piezo scanner. The piezo scanner is like an AFM. They can just use the same probe to scan in on the surface. It will help you to understand the surface topography in the nano and the micro scale. So this you can scan. So this is the post indentation image. You can see the cracking here, right? So this just helps you to understand, even you don't have SEN and TEN, you still can see the cracking. Then you can calculate the fracture toughness. This is very useful for the hard coating thin film, right? And this is also useful as to measure some mechanical properties on metal, on alloy. You can see from the we call the amorphous material. You can see we call the pile up of the material after the indentation, right? This is about the in situ scanning technology. So we have the scanning probe microscope, and we have a high accurate transducer to do the nanomechanical testing. It will allow us to do many different things, like the normal nano indentation in nanoscale, and it can help us do the tribology testing in also the nano microscale. So I will go for some example here. So we have many different standalone machines. As I said, in situ is our philosophy. So all the machines here, we provide in situ SPM as a standard. And we have the high accuracy transducer to do the real nano and the microscale mechanical research. So that is our philosophy, our core technique. And I think we have the TI Premier 2 in here. PJ will run the demo in the afternoon. So this one is also a very useful machine for the dental research. Okay, this is the introduction about our in situ technology, more about the indentation. But we also have the nano tribology test. So this is the transducer technology we call a capacity transducer. Normal indentation, we use the capacity transducer to apply the static electrical force by the capacity transducer. So this transducer can output the nanoscale force and the displacement information to us. If we make the transducer like this way, so we have the force in the normal direction. We also can get the force in the horizontal, we call the lateral force. So this will output the two direction force and the displacement. This will allow us to do the tribology testing, we usually call the scratch. The tribology testing in the real micro and nano scale. How can we use this? So typically, we have two different ways to use this transducer. One is we keep the constant load to doing the scratch, right? So with the scratch, we get the normal force and the lateral force. So lateral force is about the tribology behavior from your material. It's easy for us to get the sliding friction, plowing friction. Also, if you are care about the coefficient of friction of your material, I think this one is the most common mode we are using. The constant force scratching for the nano and the micro scale. We call the nano scratch tester. So another way is that we use the ramping force. We increase the normal force during the scratch. So that means our normal force will getting larger and larger, and when we achieve almost to the interface, it will cause the thin film delamination. So this is very useful for the thin film adhesion measurement. So here is the example. You look at this is a nano scratch. We are testing on the thin film sample. So our scratch direction is going into the screen. You can see we are increasing low and more. You see there is some interesting signal here. Blue line is the lateral force, right? So if you look at this, you can see some different phenomena. Again, let us look at this again. So in situ technology is very important. If you see the video, this video tells you the story. So if you look at this, the first jump, you see the small cracking here. Second jump, second cracking. And bigger jump, just representative of the older fin, just the lamination. So if we look at this, there are many different stages. Firstly, we have the contact plastic formation from the material. Then you can see the first jump, that is a cohesive cracking. It's about the fracture toughness. So the biggest jump is about delamination. This will totally remove the thin film from the substrate. So in the industrial, they use the nano scratch to measure the thin film adhesion. I think our machine already be applied to the data storage or the semiconductor industrial to use our machine as the standard machine for the thin film adhesion measurement. Okay, so this is another example for 150 nanometer thick titanium nitride fin. You can see there is the big jump. This is for the, we call the critical load. This is about interfacial adhesion measurement. Okay, we also can do the nano wear. Nano wear allows you to apply the force and you can wear the surface back and forth. Then we can calculate the remove volume from the material. This can help you to understand how the wear properties of the measurement from our machine. Okay, this is the SPN for the nanoware. And nowadays, we are also using the nano indenter as the high-speed indentation mapping. So in previous, we are talking about the nano indenter is one indent, right? Every indent takes 5 minutes. It's a very slow technique. But the recent 10 years, it's getting popular to have the properties mapping. So we are using the high-speed indentation on the surface. It can allow you to test 6 indent per second. So this is a kind of fast technology for the nanomechanical properties mapping. So this is the example. We are using our indenter to do the high-speed mapping. We call the 1 million indent. Of course, this is extremely too much, 1 million, right? But to just give you the idea, because we are going very fast, right? Maybe 100 indent, just 30 seconds. So 1 million indent, maybe, probably we need several hours, right? But even several hours still very fast for the 1 million data. So look at this. This is Damascus steel. There are 2 different phases we can see from the optical microscope. But we can see we are using the fast indentation. We call it XPN. This is 6 indent per second. And we have performed the fast mapping for many, many times and stitch all the mechanical mapping together. So you can see this is the image we are doing from the 1 millimeter to millimeter. 1 millimeter, 1 millimeter. And 1 millimeter indent. The mechanical properties is aligned, almost very well correlate with the optical image. So this is for the macro scale. If we want to zoom in some interesting part, you can zoom into here. You can see much more detail mechanical properties here, right? Here, I think the optical image is not good, but you still can see the high resolution mechanical properties mapping here. So I think this high-speed mapping can allow us to extend our research scale. So in the previous slide, we are almost focusing on the nano micro scale. Yes, nano indenter can do a very good job for the nano micro scale. But now it can be very fast. So we can extend our scale from the 10 micron, 100 micron, even millimeter scale because of this is fast. So nowadays nano indentation is not just only the mechanical properties measure focused on the nano and the micro scale. We can use the high-speed indentation to extend the scale what we are interested in. So if you look at this, how can we analyze this, the 1 million indent data? 1 million indent data is very difficult to use the people to check each one, right? So our indentation technique, we have a software we call the Tribal IQ. This is an origin-based analysis software. This can allow you to group in the data more robustly, more automatically, right? So if we input into the Tribal IQ, there are 3 different materials, and we have 2 different interfaces here, then it will help you to group the data automatically. It will help you to analyze this high volume data in very efficient way. So now we have a very high speed indentation, and we also have a very efficient way to get the data grouping together. So this is the total solution for us to understand what it looks like. So high-speed mapping helps us to extend the scale, right? This is another example. This is rubber. This is actually the sample from the tire company. You can see there is an interface between the out tire and the inner tire. There's an interface. They have used different recipe and different material with rubber. So we use a high-speed indentation. You can see there is a clear boundary of the interface. So upper rubber, they have some particle mix. So this can be detected by our nano indentation with high-speed mapping, because we use a very sharp tip to do all the indentation in a very localized position. So if we are using the DNA, so you can get the E prime, E double prime, 10 delta. So each phase has different mechanical properties here. That's very clear, right? So nano indenter, if we want to mimic the macro DNA or macro TMA, we can just change the tip from the sharp tip to the flat punch. So flat punch tip will compress the much larger region of the material. So each region gets 1 value. So this also tells us the E prime, E double prime, and the E prime, E double prime from the upper and the inner, but only 1 value. So this data is much correlated with the macro DNA, right? So this is a good example to tell us. If you have a 1 nano indenter, you already know the nano scale mechanical properties in very detail, right? But some customer or some of our researchers, they are really think about the macro mechanical properties. They already have the macro DNA, right? Tensile testing, whatever. They didn't know how to link from the nano mechanical to the macro. And this is a good idea. We have just changed the tip. We can average the zone of we are measuring. It's a kind of average data. Then we can extend our scale. So okay, I just give you two different ideas. One is the use high speed in the mapping, and we can stitch a lot of high speed mapping to extend our scale by XY direction. And we also can use the different probe to average our mechanical properties to align with the macro indenter. So we have many different ways to extend our measuring scale, right? So this is a very important since I would like to deliver. Nano indenter is not just the nano. So we have the nano DNA, right? So we can run in the DNA, we can get an E prime, E double prime. Why? Maybe he's not happy, huh? I speak too much. Okay, so this can allow us to measure the E prime, E double prime. It's very useful for evaluate the viscoelastic material like a polymer or biomaterial. So if we also provide very high accurate temperature control stage. It can allow you to measure the modules through the different temperature. So you can see the modules change. And this is easier for us to understand the polymer glass transition temperature we call TG. Here is more example like polycarbonate. We can see the TG. If we look at the 10 delta, it's more sharp. The TG is around 150, 160 around. So this is very useful for us. And some people will say, I can test the TG by TMA. That's easy, right? But how can you test the thin film TG? If you coat in a fin, it's very thin, only few micron, few nanometer. It is not possible for you to pull off the fin to use a TMA, right? Nano indenter will be the only one solution can measure the TG for the polymer in the micro nano scale. So this is a PDMS. So we also can cooling down our temperature to minus 100, minus 120 with the liquid nitrogen. So you can see the TG, some material, some polymer, the TG is below room temperature. I think nowadays, nano indenter still can help you to understand the mechanical properties by different temperature. And thin film, we can measure the thin film with the continuously measurement. I will go through this detail in my next session to avoid the substrate effect, right? So we have the high-speed mapping. We have the depth profile. Then we can use the mechanical property, nano indenter doing something like the mapping with the different depths. It's like the CT. We call it mechanical CT, right? So all the mapping with different depths. So if you sample with the depth gradient, this will be very useful technique for you to understand how we go for the mechanical properties mapping with different depths. And fracture toughness, we have in situ SPN. We can measure the crack length by post SPN image. We can calculate the KC, the fracture toughness, by our machine. You see the formula is quite simple. Elastic modules, hardness can measure by nano indenter. Force is what we apply on the probe. And critical length can be measured by our SPM image. If you use Pico indenter, you can measure by the SEM, right? So everything can measure by one machine. You get the KC, right? So this is another example. This is about the same thing, right? When we indent, you see the delamination from the SPM image. So you can use the high-speed mapping to see the delamination signal. So mechanical properties, again, in situ is very important. This is the beam test here. So we use the focused ion beam to cut the sample. This is the 3D IC. We want to see how strong the 3D IC. We use Pico indenter with the conical probe to do the bending test. Then bending test, we can see how the crack grows by the bending. The mechanical properties can be recorded right here. Okay, that is our core technology for the nanomechanical testing. As a feature, we have a very good in situ technology. We have a standalone system. We also have a semiconductor used. We have the Pico indenter. This is another machine to put into the SEM to allow you to see the real video. We can work with the SEM automatically with the rotating stage. We can work with the EBSD EDS with the rotating stage as well. So everything is very robust and very convenient for you. You don't need to put your sample in and pack out and put your sample in again. You can do everything in one chamber. We call the one chamber solution. Then we can do the EBSD EDS mapping with the mechanical. That's what we call the one chamber solution. And we also can do the highest temperature measurement inside of the SEM. This is the silicon carbide within 1,000 degrees Celsius. And we are doing the indentation on silicon carbide. Cryogenic inside of SEM, so we can do the minus 160 degrees Celsius for the pillar compression. All right? So this is my summary. I think we are the only company provide whole nanomechanical product line, including the SEM standalone system. We are also the only company provide the semiconductor fully automatic nano indenter in the factory. So indentation in the nanoscale, we can help to understand the mechanical properties from the harness, elastic modules, fragile toughness, and we can also do the high-speed mapping with the more wider range and extended scale to micro to millimeter. And we have nanotribology to help us to understand thin film adhesion, coefficient of friction, and also in semicon we have some structure testing for the bump. At temperature, we can measure the CTE, TG, and also the mechanical properties across the different temperature. So this is my first presentation today, and hopefully this help you to have more idea about what is the most advanced nanotechnology for the mechanical properties measurement. Yeah, this is my first slide. Thank you. Any question? Very quiet.
มีคำถามก่อนไหมคะสำหรับเซสชันนี้ก็ถ้ามีคำถามหรือว่าต้องการสอบถามข้อมูลอะไรเพิ่มเติมก็เป็นหลังจากนี้ก็ได้นะคะเดี๋ยว เราจะเบรกกันก่อนสักประมาณ10 นาทีนะคะก่อนที่จะมาต่อที่เซสชั่น2นะคะเดี๋ยวขอเชิญทุกท่านรับเบรกที่ด้านหน้าได้เลยนะคะแล้วเดี๋ยวเรามาต่อกันที่เซสชั่น2จะเป็นในส่วนของการเทสในส่วนของกลุ่มของงานตินฟิล์มนะคะก็ผู้บรรยายจะเป็นทางจิมมี่ต่อเหมือนเดิมนะคะค่ะเดี๋ยวขออนุญาตเบรกสักประมาณ10 นาทีค่ะ กลับมาครบกันทุกท่านแล้วหรือยังเอ่ยเดี๋ยวอาจารย์ขออนุญาตเริ่มในเซสชันที่2เลยนะคะเพราะว่าเดี๋ยวเรายังเหลืออีก2เซสชันในช่วงเช้าเนาะสำหรับเซสชันที่2นะคะก็จะเป็นในหัวข้อการวิเคราะห์ในกลุ่มของงานตีนฟิล์มนะคะก็จะใช้เวลาถึงประมาณ 11:20 นะคะแล้วเราก็จะต่อที่เซสชันที่3นะคะจะเป็นการวิเคราะห์ในกลุ่มของงาน Biomaterial นะคะแล้วหลังจากนั้นตอนช่วงเที่ยงเราก็จะพักเบรกทานอาหารกันนะคะก็ทางเครสมีจัดอาหารกลางวันไว้ให้ทุกท่านนะคะก็เดี๋ยวรับอาหารกลางวันแล้วก็รับประทานอาจจะเข้ามาที่ห้องก็ได้นะคะหรือว่าอยากไปนำไปทานที่มุมไหนก็แล้วแต่ตามสะดวกได้เลยนะคะแล้วพอหลังจากนั้นช่วงบ่ายนะคะเราจะเป็นเซสชันในส่วนของการไลฟ์เดโมนะคะไปดูที่ตัวเครื่องนะคะจะอยู่ที่ตึกวิจัยนะคะตรงด้านหลังนะคะที่ชั้น5นะคะโอเคก็ขออนุญาตเริ่มในส่วนของเซสชันที่2นะคะส่งต่อให้กับทางจิมมี่ต่อค่ะ
Thank you. Yeah, okay. So this is my second session. I will talk about more deeper about the micro nano indenter with the properties mapping. We already show some case in previous presentation, and I will go deeper. How do we do this in this presentation? And I will also talk about some thin film measurement application. Yeah. So if you have a question, just let me know, and hopefully we can have some interaction. Okay, so let's start from the indentation. It's I think it is from the older paper. You know, this is the paper from the 2018. So it's around 7 years ago, right? So at that time, you see the paper, they always publish the data with 1, 2, 3 indentation, 1, 2, 3 indentation, then they publish, then get the paper release, right? But now, I think it is very difficult to show this kind of data to get the paper published. Because I think we start using the high-speed mapping, and this will be very, very popular now. And this is the case we are showing for the steel with 1 million indent, right? So if you look at this, we performed the high-speed indentation by our technology. And this is very popular right now, and customers start using this for the multi-phase material measurement, also the composite material measurement. But how can we perform this methodology, and how can we get a good mechanical properties mapping? This is not just only the work, you press the button. You still have some knowledge and the background about your testing plan. So firstly, if we look at the normal indentation, you can see this is the elastic deformation. So that means you go in the indent, this is load and displacement. And when you pull the data, the displacement back to the zero. That means this is a total elastic recovery. There is no any plastic deformation. And this B case is the most case that we indent, right? So you can see the load and unload. When we get the force zero, they still have some remaining displacement. That is the deformation of the material. This is we call the plastic deformation, and this will not recover anymore, right? So look at the volume of the material, the stress influence. It's very interesting. You know, the elastic zone start first, and there is no plastic zone. So that means when you go deeper and deeper, the elastic zone is actually go further than plastic zone. So I think the volume for the elastic zone is much larger than plastic. This is very important for us to understand. And another thing is we also need to think about the probe size. You know, if the probe is sharper, that means the stress will be more concentrated, right? It's easy to cause the plastic deformation. So if your probe is blunt, not so sharp, then the plastic deformation will appear later, right? So that means the most important thing for us to understand is about if we want to do the properties mapping, we want to make sure the indentation mark of all tests is separate. We cannot indent on the same position. We cannot indent overlap for the indentation mark. So how do we decide the pitch between each indent? It will be very important for us. For example, if we look at this, we want to make sure all the plastic deformation is not overlapping. This is very important because if you are very close, you will see that all the indentation mark mixed together. The data cannot be accurate. So if we look at this example, you see this is the indentation spacing. So once you get the indentation very close, the data becomes messy and not so uncertain. So once you separate enough, the data becomes stable. This is the one thing we need to define before we process the properties mapping. Okay? Secondly, is about if you are the multi-phase material, then you can see the boundary will also affect our data. That we call the size effect, right? So we want to make sure the elastic zone will not exceed the boundary. So how we control the elastic zone? Of course, we need to control the depth here, right? For example, this elastic zone is too big because this is over the boundary. The data you get, the modules is not what we want, right? So if you look at this, you can see the hardness, the modules influence is different. For this, I think the modules is already mixed with two material. For hardness, it's still in the one zone. So of course, the data will be more uncertain because we don't know where the elastic and the plastic zone will exceed the boundary. So we also need to consider about what is the phase size. Then we decide the pitch for the indentation. And this is also about the contact depth, right? But if we only make a very slightly indent and without any plastic deformation, and that will be easy because there is no indentation mark. Then we can do very close indentation. Then we get a very high resolution image This we call the modules mapping. But you are not going to get the hardness value because you don't have any plastic deformation here. So modules mapping, you can see the pitch. No matter the pitch, how small the pitch is, the data is very stable, because there is no deformation. We don't need to consider about the indentation mark overlapping problem. So that's it. Just this slide just explain how difficult, not difficult, how many things we need to consider before we start the properties mapping, right? So this is another thing we need to consider, just as I mentioned, the different probe has different stress concentration. The sharper the concentration is higher, right? So if we look at this, this is just 3 different probe. One is 35 nanometer radius, another one is 80, another one is much larger, more than 500 nanometer. So this is the indentation data measured by the standard sample we call the fused quartz. So if we look at this, the quartz hardness is around 9 gigapascal, right? So before the plastic deformation, you cannot get the hardness value. So this is the reason why you see the data from almost from the bottom to the stabilized zone. So the stabilized zone is what we want, right? So if we look at this, I think the smaller tip, they stabilize earlier. Earlier means shallow depths. So it's around from the 15, 20 nanometer, it's getting stable. That means because the sharp tip, they can get the press deformation earlier. For the larger tip, the stabilized zone is almost close to the 100 nanometer. It will later, because this is burnt, then you can get the plastic formation later. So selecting the probe is also very important. If you want to get the shallow indent, you need a sharper probe, and you can get the very shallow area of the hardness value, right? So this is also the influence our mechanical mapping pitch. So this is an example for the just for the 1 million indent. This is no, this is a 10,000 indent. So 100 plus 100 indentation. So if we look at this, if you want to do the perfect properties mapping, you want to make sure all the indentation marks are separated, and you have to study some work. Firstly, you want to know the indent. You can see this is softer indent. This is a softer material. This is a harder material. The same force, indentation mark is different. So we must understand the softer phase. How is the relationship between the force and the indentation mark? Then we decide the pitch by each spacing. Then you can get the perfect indentation mark. So this is very important for us to understand. How can we make the good properties mapping? We need to understand the material phase size. We need to understand the material mechanical properties a little bit. And we need to understand how much depth we want to go and what kind of size of probe we need to select. So everything is linked and relative. Once we understand this technique, then we can go further to do the high-speed mapping. Okay, so this one, you need some experience. You need some practice. Of course, PJ maybe after his report, we'll talk about some data about the properties mapping, and he will go in for the demo this afternoon. If you have any question in detail, just ask Dr. PJ Wei. Yeah, of course, we have the new software and controller, and also the high-low, low-low transducer can allow us to do the high-speed mapping. And we also can perform the high-speed mapping in SEM as well, right? So this is a video for the high-speed mapping. This is the real speed. We don't isolate this. This is just a real image, almost 1 second per indent, 1 second inside of SEM. So for this, you can see the very clear image for different interface, different phase of the material, and you can see the mechanical properties after the high-speed mapping. This is an example for the EBSD, EDS. So this is much more useful, you know. If you are the researcher for the metal, alloy, composite material, probably you want to use the SEM with the EBSD to EDS to understand what is the composition, what is the grain orientation, right? Then this will correlate the mechanical properties with the material orientation or composition here. So this is what I show the video in the previous slide. So in our Pico indenter, we have the pattern technology. It allowed you to install the rotating and the tiered stage inside of the SEM. So you can import the SEM image here and see the SEM topography, then specify the zoom you want to do the mechanical testing. And this will tiered here to do the nano indentation automatically, then go back to see the poster image. Yeah, it's quite robust. And EBSD, the same. EBSD, we need to use the rotating stage. Just turn 90 degrees and go back to the E-beam to see the poster image. This is very powerful. If you can capture the EBSD image first, then our system is calibrated with the SEM. Then you can do this. I capture the EBSD, then you can get the post topography image, mechanical properties mapping, and also EBSD at one chamber. And you don't need to vent the SEM to take a sample out. You completed the testing here. And this is also the example for another material that has a high-speed mapping inside of CEN. So you can see this is a EBSD mapping. Okay, so this is another case we call the high entropy alloy. Right? High entropy alloy, they have different phase. So if you look at this is FCC and the BCC phases here. This is around 4 gigapart and 6 gigapart. We add the heating stage, we can perform high-speed mapping in different temperature. Also, we can go for the 400 degrees Celsius. So you can see this is a high entropy alloy. You can see the FCC phase. The hardness is almost no change from the room temperature to 400 degrees Celsius. And then BCC phase, it's a change from the 6 gigapascal to almost 5.5 gigapascal. They drop significantly. And you can see that's is the experiment. So as I mentioned, it's very important. But you image if this is 140 points. If you get 140 points data and you want to analyze this FCC, BCC manually every time, and 300 you have to repeat the work again. 400 you repeat the work again. It's very time consuming, right? Although you have a student can do this kind of labor, but I think a student will complain. Why? My daily life is just doing the click and analysis the data individually, right? To group the data is a kind of the time-consuming work. So we have the tribal IQ, as I just mentioned, we can group in the data by our tribal IQ automatically. So if you look at this is 1 million indent data. So if we already know have 3 different material, one is the very high martensite and the other one is the binite phase. Of course, different phase, there is an interface, right? We cannot make sure, maybe some indentation location just the interface. So we need to treat interface is another different phase. So totally, we input 5 cluster, 3 from our different material, 2 from the interface. So you can see the tribal IQ running very well. They just help us to grouping the 1 million indent here. So phase 1, phase 2, phase 5. This is modules, and H is hardness. So this is the value. Okay, so we got a question from the customer. Do we need 1 million indent every time? Of course not, right? 1 million is time consuming. So we pick up 10,000 indent from the 1 million indent. So we use the tribal IQ to run the 10,000 data. You can see the value between each phase is very, very correlated, almost the same. This gives us the idea. So how many data is enough? Maybe 10,000, maybe 8,000, 7,000 is enough. You can try, because tribal IQ is very fast. He can just go output and analyze data within the minutes, within the second, right? So you can do a lot of different analysis. The key is that you already get the raw data here. So this will help your research in more efficient way. So now our tribal IQ already have a lot of different application for the nano indentation, high-speed mapping, scratch, everything. So I think we have a Premier too here, right? We have a tribal IQ with Premier too. So probably we can try. Okay, this is my first session. I still have 10 minutes, right? Secondly, I would like to talk about high thin film measurement. You know, for the thin film measurement, we know we have some challenge we call the substrate effect. This is the contact depth of the nano indentation. This is a thin film sample. When you go deeper and deeper, your stress will penetrate over the interface, and your substrate start deformation. So that will influence our hardness the modules data. We call the substrate effect. So typically, if we look at the paper, the contact depth divided by the total thickness, and this is the modules value, almost 10% of the fin thickness, you start seeing the substrate effect. So for the thin film sample, the challenge is the fin thickness. We have the function we call the CMS. That's CMX. This is a continuously measurement. X means hardness modules, whatever. So we can continuously measure the stiffness. We can continuously measure the hardness. We can continuously measure the modules as well. So this allowed you to do the indentation like the drill machine here. So this is actually, if we look at the low function, just like the nano indenter, normal, low and unlow. But we added the oscillation in the H segment. So if you zoom in here, you can see there are high frequency acceleration during the indentation. If we can treat one oscillation as one small indentation, then we can calculate the stiffness from the one oscillation, then we can calculate the modules and hardness for each small oscillation here, right? So this will allow us to measure the modules and hardness by depths continuously, right? So this we call the mechanical properties depth profile. So this is very important for us to understand when the substrate effect starts. So this is two examples with the same fin. You can see the yellow fin. We start from almost 10 nanometer, and it's very stable until 40 nanometer. The hardness start drop to the substrate, transfer to the substrate. Then yellow fin, I think he start from almost 20 nanometer. So if you don't have idea about your thin film sample, you need to use the CMX first to understand when you are going to get the substrate effect. This is very important, right? So, of course, for yellow, I think the fin is thicker. If we have a 10% rule, the fin thickness is around 400 nanometer. Probably yellow, grade one is 200 nanometer. So this is very important for us to understand. So we are trying to apply this for any different kind of resolution, the solution of the thin film. This is another example. We are using our transducer to measure the ultra thin film mechanical properties. You can see this one is the 23 nanometer. It's very thin, right? So the substrate effect will probably only 2-3 nanometer. Very difficult. So you can see if we have a very sharp tip, and very well calibrated area function, we can get almost 1-digit nanometer data. So you see the substrate effect start very, very early, around the 5 nanometer, right? Almost 5 nanometer. This is hardness modules. So this can just help us to understand. If you don't have the continuously measurement, you are not going to get the result. Probably you select the wrong data here, you get the modules in different range. So this is very important. And this is also the data we call for the protective fin of the protected cover glass of the thin film. Even this one, you see the 250 nanometer. If you don't use the sharp enough probe or ultra high resolution transducer, you only get the data here around 30, 40 nanometer. You don't see the plateau, the flat, stable area. You cannot get the intrinsic thin film properties, right? So this one is the glass. This one is the thin film with glass. See? You don't see the plateau area, you will not get the mechanical property, intrinsic mechanical properties. Okay, this will be the next topic. I'm not going to go through it today. Because all the machines, they have the limitation. So if we cannot get the shallow indent enough, sometimes we need to use the model to do the fitting. So this red line is the model to fit in the silicon nitride hardness, right? So you need a model. But before you are applying the model, you still need the raw data of the depth profile, right? So this is for the ultra thin film measurement. Okay, not only for the fin thickness, for the thin film, a lot of people, they are also concerned about the fin delamination, fin fracture toughness. This is a very important topic. We already showed the example in my previous presentation about the pop-in. So this is from the paper. You can see when we are doing the indent, this is the normal indentation. When you can see the pop-in, you see the cracking. So you can get this from SEM or from our SPM image. Also, you see the cohesive crack and the cracking growth by the penetration. Sometimes you see the delamination. You see, this is the fin just delamination happen. Okay, so this is an example you can see more clear. So this is the data we are using the indenter to do indent into the thin film. You see the crack pop in signal here, and you see the adhesion, right? So if you look at the cross-section or by the SE image, you can see the cohesive crack is usually happen first. Then second pop-in is the delamination under the surface. Maybe you cannot see from the surface, but if you cross-section, you see the delamination happen. So that's very interesting for me. If you have crack pop-in, you can use model to calculate the fracture toughness. If you see the delamination, you can use the model to generate the adhesion work, adhesion measurement. So here is the example. We see the pop-in, right? But we don't know, is this the crack or this is the delamination? We need to find the evidence. So the SPM, in situ SPM will be your best partner to find the evidence here. So when we find the pop-in, then we stop indentation. We start doing the SPM imaging. We can see there is a step. It's very clear the fin just totally delaminate. And substrate is here. And this is fin. So we can measure the thickness, the step height, by this cross-section. You can see the step height is almost 147 nanometer. What does that mean? Our customer told me their fin thickness is 150 nanometer. So we almost can very confident that say, okay, this pop-in is the fin delamination totally. So how can we use this pop-in? We can use this pop-in to characterize the fin adhesion measurement, right? And we also have the high-speed mapping, right? So we can do the high-speed mapping. This is 100 indent. You can see the pop-in is quite repeatable. Pop-in is quite repeatable. So if we use the critical low here, we just pick up the start point of the pop-in, and we use the 100, then we can do the critical low mapping. What does that mean? This can be means adhesion mapping. So if we look at this, this is the display application. So there is the transparent coating, so you cannot see the transparent, but you can see the from the SPM image, because there is still some pattern underneath here. So if we just use the high-speed indentation, we can see there are two groups and also the interface. Two groups, critical low, and we can see the critical low mapping. Does that make sense? Yeah, it should make sense because different material, they have different adhesion properties. So this is just a very interesting application. Just want to let you know. Nano-indenter is not just only for the harness measurement. Some the pop-in, some the critical low is very useful for us to evaluate the thin film properties. Fracture toughness, that is also what we are saying. You need in situ technology to see the crack length, right? This is my topic today. Of course, I just want to help you to have more idea. Nano-indenter is a very useful machine for the nanoscale material mechanical characterization. And we can use this for harness modules measurement. We can use this for fracture toughness and also the adhesion measurement. And we have many different technology. If you have the SEN, you can use the focused ion beam to cut different shape of sample. We can also prove the nano tensor testing, tribology, heating, high-speed mapping. So this is my takeaway. So the first session, I talk about how to select the pitch for high-speed mapping and how to analyze it. And second is the depth profile can avoid the substrate effect for the thin film measurement. And most important thing is that pop-in signal. Sometimes we want to pay more attention on the pop-in. It is not a noise. It is something happen on your material. If you can use this data well, you will see different things about your mechanical properties on your thin film material. Okay, that is my presentation today. And thank you for listening. If you have any question, just let me know. Thank you.
Thank you. I'm honored to be here to share some experience and applications for biomaterials and some polymers. And I hope if you have any questions at any time, please interrupt me. It does not bother me at all, so please feel free to interrupt me if you have any questions. Okay, so I would like to start with this slide for today's discussions using the range of the modulus to take an overview of our biomaterials and polymers. So we can see the total range in the viewpoint of the modulus. The total range could be 4 magnificence, 4 orders. So the very high modulus could be coming from the bone, the teeth, And the lowest modulus could be coming from the tissues, hard veils, hydrogels, and we will cover the range for today's examples and applications. Okay, so firstly, let's focus on the biomaterials with high modulus, which is a stiffer or strong materials. So the very first example I would like to show here is a shell structure from a kind of seafood creatures. And you can see that we cut the one portion of the shell and well mounted, well polished. Then we pick up a specific area here. In the optical microscope, we can see there are two different regions with different colors. So we use our nano indentation to make indentation array to characterize the hardness and modulus distributions, just like Jimmy mentioned about. One single indent can provide us one hardness and one modulus. So if we perform a lot of indentation tests over this chosen area, then we can have a lot of modulus, a lot of hardness with their corresponding coordinates. Then we can have this color map to get the idea of the modulus distribution together with the hardness distribution. So typically we use this color map to represent the mechanical property distribution. So we use a warm color to represent high value, and on the other hand we use a cold color to represent a lower value. So this is the modulus map, and this is the hardness map. And here we have totally 400 indents performed crossing this area. Therefore, we have totally 400 hardness and modulus. So besides the maps, we can also have the histogram to see the peak value for these two components, for example, here. So we can see that this is for the higher modulus, represents the mechanical properties of elasticity of this component on the right-hand side for us. So the mean value of the modulus is around 70 gigapascal. But on the other hand, if we take a look of this peak on the right-hand side, on the left-hand side, sorry, and the peak force, sorry, the average value for modulus is only 10 gigapascal distributed in this region. So we get the idea of the distribution together with the mean value to take a look for looking at the peak value of histogram. Similarly, we can do the same thing to the hardness. So again, this is the mean value of the hardness on the right-hand side, which is 3.1 gigapascal, which is higher. And on the other hand, for this portion on the left-hand side, the hardness is much lower to be only 0.6 gigapascal. So this is a very easy thing to understand this pickup region for two components, especially in this shell structure. And then we can go to another interesting region. Again, we select this region because we can see different colors in these, three different colors in this region via optical microscope. So we have this one, and this one. So we can make, again, 400 indentation by 20 by 20 array. Then this is the modulus map, this is the hardness map. Again, so we have the I have the medial region which has the higher modulus and the higher hardness. So the mean value, the peak is here, And we also have a median mechanical properties of hardness and modulus, which has the peaks here for hardness and the peaks here for the modulus. And on the right-hand side corner, up corner, we have the lowest hardness and modulus distributed here, contributed coming from the third component. So the mean value is here. So this is the idea I would like to show to you. Using the technologies Jimmy just mentioned about for us, we design the indentation array, and we pick up an interesting region to make the indents, and then we can get a large number of hardness and modulus. Therefore, we are able to have the hardness map, modulus map together with the histograms. So this is the very first example I would like to show to you related to the biomaterials with higher mechanical properties of hardness and modulus. So this is for structure of shell. And the second one is maybe more interesting to most of you. It is a component of tooth, mice tooth. We call it enamel, which is the outer structure of our tooth. And then we pick up this one. So again, this is a sample of mice tooth, well mounted, well polished. And we pick up this area. And before we have the indentation results, we also have the information of the chemical composition measurements. So we can see there are two elements. One is calcium, marked by green color, and the other one is iron, marked by the blue colors. And if we take a look of this distribution of chemical elements, we can find the interesting distribution. On the very top of the enamel, there is a very thin top there of iron rich, and then we have a calcium rich in the middle, and then at the very base and the bottom region we have the fully cadmium. And then if we again design a indentation array with a rectangular area, then we can have the modulus map, hardness map together with their histograms. So again, we can just correlate the mechanical property distributions together with the chemical distributions. And we will find the correlation will be the iron-rich top there will lower the hardness and the modulus a little bit. And then in the middle, the calcium-rich area, the modulus and hardness are also median. And then at the bottom, if we have fully 100% calcium, the hardness and the modulus will have another distribution. So it is very good correlation if we have the suitable resolution with the hardness and modulus. And it is not very difficult for us to use our nano indenter to make the indentation array. Then we can have these very highly correlated mechanical property distributions. So we can combine the viewpoints of the mechanical properties together with the chemical element distribution. Okay, so this is the two examples I would like to present. I would like to share to you talking about the biomaterials, actually biocomponents, composites with higher mechanical properties. Then we can move to another region of the mechanical properties with a very low modulus. And I mean, in order to measure them, typically we will use a specific probe together with a specific indenter. You can see that sometimes we have a product line providing the transducer attached with the optical microscope. So for some researchers or biologists, they are much more familiar to use the optical microscope. So this option could be more friendly to them to get into the world of nanoindentation. So this is the very first one I would like to show to you. Talking about the biomaterials with extremely lower hardness modulus, sometimes we will use a very blunt indenter for testing them. This is the idea. So if we have a, for example, tissue sample with different components inside there, if we have if we are using a very sharp indenter, the good thing is we can have a very high mechanical resolution. But another thing will be we will see a lot of different mechanical properties, contributed by different components. So if we use a blunt, much blunter tip, for example, a large radial spherical probe, or even a flat punch one, just like the example Jimmy just gave us, talking about the tire example, if you still remember, we are able to have the mechanical property in the overview, overall viewpoint. So we will have the average mechanical property. So that will be provide us in a different kind of understanding for biomaterials. And yeah, so I would like to use this to give a very rough idea about this. So if we use a very sharp tip, we are going to here. And if we use a very blunt probe, probably we will doing this. So there are different kind of applications, different kind of considerations, different kind of requirements for resolution for the detailed composition understanding. So this is the very first example I would like to show to you. This is a single cell of neural network, and it is quite big, and we use a idea of two parallel plates compression tested to observe the mechanical properties. So in this case, we will have an overall understanding for this cell. So of course, the cell could have a outer layer we call central membrane, together with some liquid-like within structure. And then we have a very large flat punch probe to make indent onto one single cell. That means we are using a parallel plates compression idea to test the mechanical property of the single one cell in the overall viewpoint. So this is the idea in the design of this kind of mechanical testing. So we have the stress here and strain here. So we can understand this compression test to be a uniaxial compression test. So we will have a elasticity measurement. Typically in the material science, we will use Young's modulus to represent this idea of elasticity. So you can see that we can use different size of the flap punch together with different substrate. I mean, we can place our cells onto different materials of substrate. Then we can make a lot of single, compression tests for, of course, for a lot of different cells. And this is the results. So we can see that it is coming from a PhD thesis. So we can see that the effect of the substrate material. So if we're using a glass, which is a very regular, typical substrate to place the cell, the modulus will be higher compared to use a softer substrate material of PLL. I don't know what exactly the PLL is, but I believe this is a kind of plastic material. Then you can see the substrate material will definitely affect our modulus measurement due to the lower stiffness coming from the substrate itself. So it is one example for us to test a biomaterial or biosample with extremely low modulus. And we can apply this similar idea to another different work. This time we change the size of our plate punch to see the effect. So if we use a smaller size of flat punch to do the compression test, you will see the stiffness is lower. On the other hand, if we use a larger diameter for the flat punch during the same experiments, the contact stiffness will be higher. And we apply this analysis for modulus calculation, then we will have a stable modulus coming from different flat punch probes that we use. So we are able to have the intrinsic elasticity understanding for this cell. So this is actually a brain cell, and we test them with different age for this brain cell. So this is the very brand new prenatal brain. So the myelin is not so much. So the modulus or the stiffness will be lower, maybe the lowest. And when the brain cell starts to, to develop, to grow up, the methylene content will going up, and correlatively, the modulus of this brain cell will also going up. So we get a very direct or very straightforward idea that this modulus is highly related to the myelin content for a brain cell test. Okay, so this is another one for brain cells, but it is not one single cell. Instead, it is a group of brain cells. Actually, they are cancer cells, so it is a very bad thing. But some researchers can put some some gel into this cell group, and then we can take a look of their mechanical property changing with these microglial contents. Again, if the percentage of this gel increased, the stiffness and the modulus will getting higher and higher. So it is a very direct observation for the brain cancer group behavior in the viewpoint of mechanical properties. And on the other hand, we can do something more interesting in the viewpoint of mechanical property. The first thing is we call the creep behavior. That means if we hold the applied force for this group of cancer cell, we will able to detect the increasing displacement. So this behavior in the material science called creeping. So we collect the displacement change with time when holding the applied force as constant. We are able to have this creeping behavior detection. After that, we use this model to characterize this creep behavior. So we have totally three components in the viewpoints of mechanical properties. One is the elastic modulus. The other one is a Kelvin series, including a stiffness together with a damping coefficient. So the stiffness means the modulus, another modulus, and the damping coefficient means the viscosity. So it is an idea of viscoelasticity understanding. And then you can see here is the modulus of this independent stiffness. So we have this one, and we have this E sub 1 to represent the elasticity within the physical elastic. And we have the damping coefficients here. And we compare this understanding with different percentage of microglia. Again, we can see if we have a higher jaw composition in this brain cell, the damping coefficient will be higher together with this one. So we can get the idea that this composition of microglia increase actually is a positive effect or influence to this viscoelastic distribution in the mechanical property of these cells group. And the second one is another way we call relaxation, which is trying to hold the displacement of this indentation test, and we record the force decreasing with time. So this behavior is called a relaxation or a stress relaxation. So again, we can get the idea of the influence of this percentage of microglia. So we can see in 10%, the relaxation time will get longer, much longer than 0%. So it's just another maybe not straightforward, but detailed and interesting to me understanding for the cancer group of cell to connect it with the viewpoint of mechanical properties. And yeah, this is another thing. We can use an isolation force, that means here, like this to get the understanding of the mechanical properties in dynamical mechanical analysis way, we so-called DMA understanding. So we are focusing on this one. We called loss factor, or simply time delta, which is the ratio of the loss modulus to storage modulus. Again, we have different percentage of microglia, and we can also change the oscillation frequency and see the effect of this 10%, only 10% higher percentage of this microglia, and we can see the effect in the viewpoint of DMA. So this is the idea for combining the mechanical test into the bio material. No matter your biosample is one single indent with a big size or a group of multiple cells, we can apply exactly the same idea to test them in the viewpoint of mechanical properties. Okay, so I would like to give a very a short conclusion about the very first section for my sharing today, talking about bio samples, biomaterials. So we all know Bruker actually has two main product lines for our division. One is nano indenter, and the other one is AFM, atomic force microscopy. So for using an AFM, because the tip of an AFM is typically very sharp and very, small aspect ratio. So using an AFM for bio testing in the viewpoint of mechanical properties, we are almost doing this. So the good things, the main advantages for AFM testing is a very high resolution. But the bad thing is if the bio sample, for example, a huge cell is big enough and very complicated inside the structure, the structure or bio components, you may not get the total understanding of the big scales, and use nano indentation because we have a typically blunter tip and higher applied force. So we are here. So typically we test a bio sample in the overall viewpoint or an average understanding for the entire bio sample. So that will be the very short conclusion for the first section of my presentation about talking about the bio materials. So secondly, I will move into polymer samples. So the very first example, actually the only one example I would like to share to you is talking about the dynamic mechanical analysis, DMA for short. We typically use DMA test to get the idea of we so-called the viscoelastic understanding. So for a lot of polymers at room temperature, the viscoelastic properties are very significant. So that means they are very very sensitive to speed or to rate. So the first viewpoint I would like to share to you is the pool of force test. So it is the idea. So we will get the probe far away from the sample at the beginning, and then approach the get down the probe to approach the sample. Then we will have we so-called jump into contact point like this if the sample surface is viscoelastic. So we will have these things happen typically very suddenly. So we will have this B point we typically called the jump into contact point. And then the probe starts to get contact with the sample surface. And then we increase the force, then the tip will penetrate into the sample deeper and deeper. Then we unload the force. But at the very end of the unloading segment, we will have a very large, typically, we call the pool of force to be the maximum attractive force, and then going down to, totally out of contact. So this is the entire, we so-called 4 stages of a pool of force test. It has another name, actually, in FN respect. We will have another name we call the force testing. Okay? So this is the very first example I will show to you, talking about the rate sensitivity or the speed sensitivity. So we use exactly the same force to test a uniform polymer. And then you can see that we just change the time for the testing. So we can use a very high speed. We get the results as the blue curve shown here. So you can see that the pool of force is much, much higher than the results collected using a long testing time. That means a extremely lower speed. So that is a very first example I would like to show to you about the polymer characterization, which is we so-called rate or speed sensitivity. So it is a very special or very important points for mechanical property understanding of polymers. Because typically in a lot of applications, when we talk about mechanical properties, we will not mention about time effect or speed effect. But for most of polymers, even at room temperature, the rate sensitivity is very high, it's very significant. So it is the very first example I would like to show to you. The same probe, the same testing, the only difference is increase the speed or decrease the speed. You will find the mechanical response will be very different, which is related to the speed sensitivity. Okay, so another viewpoint that we can see this effect of rate sensitivity is we say this is a partial unloading method. So the load function will be something like this. We use different cycles to get the loading, holding, unloading, and then do it again and again. So the very interesting observation point is if you take look of the unloading segment together with the next reloading segment for the next cycle, you can see there is 2 different material response. The blue dots are coming from a pure aluminum, which is not so rate sensitive at room temperature. And the other one is a very typical polymer, polycarbonate, shown here. So if we take a look of the unloading and the next reloading curve collected from polycarbonate, you will find it is very interesting because they are not overlapped very well. So this is the unloading, and then reloading will go another path to the next cycle. So unlike aluminum, you can see there is almost 100% overlap when unloading and reloading. So that is a very strong evidence, a very good observation point for us to get the idea or to judge the speed sensitivity for our sample of polymers. So this is non-overlapping behavior is typically so-called hysteresis. That means they will be different when decreasing the force or increasing the force again. And a good way to understand this kind of behavior will be we call the constant strain rate testing function, which is, you can see that the force is increased using a exponent function. I mean, the force increase with a different loading rate. So we can set up this loading rate to achieve constant strain rates. So here we apply 4 different strain rates from a very low one, the black dots shown here. So the total time for the testing will take much longer. And we also can apply a very high strain rate to increase the speed of this testing. And the material chosen here is the polylactide, PLC, I guess, for sure. And then we have these comparisons of mechanical property changing with contact depths. So we pick up the 2 strain rates. The red dots are the higher strain rates, and the blue dots are the lower strain rates. So the interesting points is the hardness. So for this polymer of polylactide, it is highly sensitive. Its hardness is highly sensitive to strain rate. So you can see that the same probe, the same penetration depth, if we use a higher speed, a higher strain rate, the hardness will be higher. And if we use a smaller or lower speed, smaller strain rate, you will find the hardness will be lower. And compared to hardness is highly sensitive, which is highly sensitive to strain rate. If we take a look at modulus, you will find another story. For this polymer of polylactide, the modulus is not sensitive to strain rate at all. So no matter higher or lower strain rate, the modulus behavior is almost the same. And in order to check this strain rate sensitivity, we can design a very special experiment to check this hardness sensitivity to strain rate, which is this. So we can design a very special low function as shown on green dots here. So we can change the strain rate. We use a higher strain rate at the beginning, and then at middle, we decrease the strain rate into a lower one for a period. After that, at the very end, we increase the strain rate to the higher value again. So this is the hardness results when we change the strain rate. So again, we see this very repeatable strain rate sensitivity showing in the hardness here. So at the very beginning, just like I say, we use a higher strain rate, so the hardness is higher. And at the middle, if we decrease the strain rate, the hardness will go down immediately and go back to the lowest hardness corresponding to the lowest strain rate. And at the very end, if we increase the strain rate back to the original level, the hardness will go to the higher value, go to the original level again. So it is also a very important observation, or maybe an interesting thing we can do. That's to take a look at the red sensitivity showing in the hardness for this polymer of polylactide. So this is the very first or the only one example I would like to share to you for a polymer indentation test. We can have another viewpoint of red sensitivity and go into another deeper observation. We are able to take a look of the total 4 different strain rates. So we have a totally different 4 hardness response shown here. And then, on the other hand, we can also have the creep testing to get the strain rate changing with time during the force holding segment. Then we have this region of hardness changing with the strain rate. So in the conclusion of this understanding for red sensitivity in the viewpoint of hardness, we will have this plot. So see, this is the relation. This is the correlation between the strain rate and the hardness. That means if you have a higher strain rate, for example, here, your hardness will be higher. On the other hand, if you lower the strain rate, if you use a slower speed to test, to make the indentation test to collect the hardness results, you will find the hardness will be lower. So that is the we so-called strain rate sensitivity in the mechanical property. For a lot of polymers, they will behave very differently. For this polylactide, only hardness has the red sensitivity, and this is the slope is actually the important parameter for the red sensitivity. Okay, so that will be the second part of my presentation, talking about the mechanical properties of polymer, especially for the strain rate sensitivity. So we can have the dynamic indentation test to get the idea of this. Very final, if we have our heating stage, there is another interesting, I can say, driving force for the red sensitivity, which is temperature. So if we have our heating stage, we can doing the similar thing at different temperature levels, then we can get another idea of the red sensitivity. Okay. Okay, so that is all the presentation I would like to share to you today. Yeah, thank you so much.